Okay. Let me start by, even though the title of this talk is about gravity and quantum information, really what I want to do in this talk is do something slightly different. I will talk about gravity and quantum information, but what I want to do in this talk is, in a sense, try and give you a sense of where I think quantum gravity fits in the structure of fundamental physics. And if I can communicate that at the end of this talk, then I feel that that's at least one objective which has been achieved. So this is how I conceive of the structure of fundamental physics, and I should say this is something which is in some sense my perspective, and not everyone might share it. This is the way I would think of the way fundamental physics has proceeded and has progressed over the years. In a sense, the study of physics has started initially with what one might call mundane physics. Mundane physics is about things that we can see and we see in our everyday life. So I should say here that I'm not using mundane in a pejorative sense, I'm just using mundane in the sense that this is about physics that we can see and feel and do experiments with in our everyday life. For example, I could ask a question of the kind, if I throw this pointer up, how high will it go and how long will it take to come back into my hand? And that's a well-defined question which you can answer. And about a few hundred years ago, we learned how to answer these kinds of questions, and we learned a lot of other things that have to do with everyday life, including the behavior of light, the behavior of gravity, the behavior of springs, and many other systems. And all of that I would classify in a sense as going under the umbrella of mundane physics. Now, about 100 years ago, people realized that partly through experiment and partly by thinking more about the principles of physics, that in fact, if you started doing some extreme things, so if you started going to high speeds, or if you had two observers who were relatively boosted with respect to one another, then some of the intuition that we developed from mundane physics doesn't hold any longer, and that led various people to come up with the theory of special relativity. And what happens in special relativity is that the notion of space and time that we've developed from our everyday intuition gets modified in a very dramatic manner. So it's not just that there are some new equations that describe physics, but in fact it is that there's a paradigm shift in the way we perceive space and time around us, and that's something that comes about with special relativity. And closely related to special relativity is the new theory of gravity that was developed just about 10 years after special relativity, which is called general relativity. And general relativity is really a theory of gravity, but in fact it further modifies the way we contextualize and perceive and think of space and time. And once again, these effects in a quantitative sense are important only if you're in strong gravitational fields or if you're at high speeds. And so they correct the equations of mundane physics in a rather delicate way, but nevertheless from a conceptual perspective, they involve a rather significant paradigm shift. Now just a few years after, around the same time as special relativity and general relativity were being developed, people also started considering atomic physics and what happens if you go to very small distance scales. And physicists developed the notions of quantum mechanics. Quantum mechanics, in a sense, involves an even more radical paradigm shift from the paradigm shifts that are brought about by relativity. And what we need to change in quantum mechanics is our notion of reality. So, remember I said that in relativity, we needed to change our notions of space and time and how we perceive them and think about them. What we need to change when we come to quantum mechanics is our notion of reality, really, what we think is real, and I'll try to describe that in some detail. And so this described. That's right. I'll try and avoid this happening. Okay, so what we need to change when we come to quantum mechanics is really the notion of what we think of as reality. And then people started asking, what if you do two of these things together? What if you take very small objects and you boost them to high speeds? And so you can start putting these regimes together. And that formalism was also developed pretty successfully. So you could look at small objects in high fields. And that formalism is called quantum field theory. And that was also developed and applied very successfully. But then one could ask the following question. You see, there's high speeds and strong gravity on this side, and there's what happens to small objects. You could ask, what if you have very small objects in strong gravity? What about the regime in which gravitation and quantum mechanics are both important? And that would be a theory of quantum gravity, And the reason I've put question marks here is because we don't really still have a complete theory of quantum gravity, and this is a question that has vexed theoretical physicists now for several decades, and it's one of the outstanding questions in theoretical fundamental physics, which is how do you develop a theory of quantum gravity. I'm going to try and flesh out this framework and try and describe to you, what I said in the past few minutes in a little more detail, and try and describe to you what the place of quantum gravity in fundamental physics is. And in the context of that, I'll also talk about the relationship between black holes and gravity and information. Okay. So let me start actually by just telling you in a little more precise sense what I mean when I talk about mundane physics, and then we'll move on to all the other blocks of that flowchart. So, in a sense, the quintessential example of what one might call mundane physics is just Newtonian gravity. It's in a sense one of the first formulas in physics that was developed, and it was developed now more than 300 years ago. And the statement is very simple, and the way that it was developed to understand the dynamics of the solar system. And the statement is just that if you take two objects and you separate them by a distance r, and these objects have some masses, then the force between them is proportional to the product of the masses, and it's inversely proportional to the square of the distance between them. And the square is another important thing, because it's something you can directly measure. You can try and separate the objects by twice the original distance, and you can check whether the force goes down by a factor of 1 by 4. And of course, one has to ask, along with this, what one means by the force. And by the force, one means the mass into the acceleration. And then this leads to some differential equations that you can solve in a well-defined way. And these differential equations actually were solved and successfully predicted the dynamics of the solar system. So this, in some sense, was the first success of classical physics. It was a very remarkable success. And in fact, a lot of the reputation of physics as this exact science and as this very successful science, in a sense, derives from the early studies of gravity. Okay. And I should say once again that I say this is mundane physics, but this mundane physics is really something that's very, very important in our lives. Every day nowadays we hear of the successes of ISRO, for example, but really the physics that the physicists at ISRO are using is just very accurate versions of Newtonian and other classical effects. They're not using, or they usually in most situations, if you're trying to look at rockets and satellites, you don't, unless except in very rare cases, need to look at relativistic effects. So what you're generally trying to understand is just the dynamics of Newtonian gravity. And the same Newtonian gravity explains not only how the Earth goes around the Sun, even though that's what it was developed for, but it also explains how the Moon goes around the Earth. And the same Newtonian gravity is also successful in answering questions like the question I started with at the beginning, which is, if I throw this up, how long will it take to come down? And in fact, all of these things are things you can compute by means of Newtonian gravity. And of course, there's a lot more that goes into classical physics, including the dynamics of electrodynamics and light, which I'll come to in a minute. But one important thing I want to say is that this thing that I'm calling mundane physics is a very broad umbrella. It's something we understand, it's something that our intuition is designed to appreciate. It's something that in a sense our brains have evolved to understand the notions of space and time and force that go into mundane physics. These are things that we understand naturally, and these are very, very useful and very, very successful concepts. Okay, but now people realized about 100 years ago that even though these were very, very successful concepts, there was still something that was lacking in them. And the thing that was lacking came from a study of certain aspects of classical physics which had to do with the dynamics of the electromagnetic waves and of light. And one of the principles people discovered, so Lorentz and Poincaré largely discovered, and Einstein later did some more work on it, even though he's often given the majority of the credit. It was really these two people who discovered that there's a very important physical principle which you should apply to make physics simple, and that's the principle of relativity. And one of the important aspects of the principle of relativity is that if you take two observers, then the speed of light remains the same for two observers who are moving at some constant speed with respect to one another. Now, this is actually a very dramatic and radical statement if you think about it. That's because if you're standing on the ground and you see a car pass by you with some speed, and you think of another observer who's also going in a car with some speed, and you know that the car has some speed with respect to this observer on the ground, but with respect to the second observer who's moving in another car which is going at the same speed, the relative speed of the first car is 0. Right? So they have no relative speed in between them. But what these people discovered was that light doesn't behave in this manner. If you look at the speed of light that you would measure, the speed of light that somebody going in a very fast car would measure, or in a very fast rocket would measure, would in fact be exactly the same. And this simple principle, when elaborated and when thought about, led to this rather vast and interesting structure, which is the structure of relativity. And as I said, one of the things that relativity forces you to do is it forces you to modify some rather cherished notions that we've developed from our mundane intuitions. And one of these cherished notions, for example, is a notion of simultaneity. So to think about this, you need to think about two observers, one of whom is standing on the ground. Okay, so this is my stick figure who's standing on the ground. And this person has two clocks. And this person on the ground has synchronized these clocks. Okay, so this person thinks that these clocks are ticking at the same rate. When this clock takes 1 second, at exactly the same time, this clock also takes 1 second. Okay, so this person has synchronized these clocks to great accuracy. But then you have somebody else who's going on a very fast train. Okay, of course, this is a thought experiment. But you have somebody else who's going on a very fast train. And one of the things that the theory of special relativity tells us is that even though the ticks of these two clocks appear simultaneous to this observer, if these clocks are spatially separated, then these two ticks will not appear simultaneous to this observer. Okay? So that's a very dramatic change from our conception of time in mundane physics. Okay? So as I said, relativity forced us to change our notions of space and time, and this is one dramatic illustration of that. Okay. But when people began to think more, they realized that relativity didn't just force you to change your notions of space and time, it could also force you to change your notions of dynamics. So in particular, you could think of, remember I told you that the force between these two, the sun and the earth, was proportional to the product of their masses and inversely proportional to the square of the distance between them. But now imagine that some huge giant, some giant from an extraterrestrial civilization came and this huge giant pushed the sun. Okay? Now this huge giant came and pushed the sun a little bit. You could ask, when will the earth know that the sun has moved? Now if you take Newton's law literally, then you would imagine that the distance between the earth and the sun would change instantaneously. And because the distance between the earth and the sun would change, the force on earth due to the sun would change. And therefore, when this giant moved the sun, we would know immediately that the sun is moving. But you see, this is inconsistent with this principle of relativity I told you about, which says that the speed of light is a constant for observers, and as a corollary, also implies that nothing can travel faster than the speed of light. And so if this Newton's law of gravitation was literally correct, then you see that it would be in contradiction with this principle of relativity. And therefore, physicists had to modify not only their notions of space and time, but also the dynamical laws that they had developed, including the dynamical law of Newtonian gravity. And when they modified that, they had to make an even more dramatic change to their picturization of space and time. And what they started saying instead, and as I said again, this is a paradigm shift. The paradigm shift they came up with was to say, in fact, you shouldn't think of the sun and the earth as exerting a force on each other. Rather, you should think of the sun and the earth as living in a fabric of space-time. So you should think of the sun and the earth both living in a fabric of space-time. And what happens here is that the sun, by virtue of its mass, bends this fabric of space-time, and then the earth goes around in an orbit around the sun, not because it finds that there is a force that the sun is exerting on it, but rather because these elliptical orbits are the natural trajectories to take in this warped fabric. Okay. So you see, the language we use to now describe simple gravitational physics becomes very different in general relativity. And as I said, general relativity was brought about because you had to make Newtonian gravity consistent with special relativity. And the language we use is completely different. We are not saying that there's a force between two objects and one object is therefore, there's a centrifugal force and therefore one object is going around the other. I should emphasize that this is not only a question of some pictures. There are very precise equations that were developed to set this up. In fact, some of the earlier pictures that I mentioned already were thought of by Riemann, but then really David Hilbert was the one who first wrote down these equations. Einstein also did some work on them, did a lot of work on them, but David Hilbert was the one who first wrote down these equations. And there are some precise equations that tell you, given some matter, the matter, this mass comes into this thing in the right hand side, it's generalized to something called a stress energy tensor. And given some matter, you can compute what the geometry of the space-time is. Okay? And then given the geometry of the space-time, you can compute how the matter would move in it. So really, relativity can be summarized in two slogans, which are, I think, due to John Wheeler, which says that matter tells space-time how to curve according to these equations, and then space-time tells matter how to move according to the equation below. So these are two equations that will summarize the content of general relativity. And I should emphasize that, in fact, the quantitative changes that general relativity brings about in, for example, solar system orbits are very small. When the shift in the perihelion of Mercury was measured, it's an extremely small effect. And it's easy to check, in fact, that there are many, many huge perturbations due to neutron gravity that are much larger than the small perturbations that brought about due to general relativity. So this is a very delicate effect from a quantitative point of view, but from a philosophical point of view, general relativity is a dramatic departure from the mundane notions of space and time that we have. Okay, let me just go back also to the question I asked at the beginning. What happens if a giant moves the sun? The way general relativity makes gravity consistent with locality, or which is a statement that no signals can travel faster than the speed of light, is that it doesn't say, as I said, that the force is proportional to the inverse square of the distance between them. Rather, the way general relativity would address this problem is it would say when the giant came and pushed the sun, this push would cause ripples in this fabric of space-time, as you can see here, and then these ripples would gradually propagate at the speed of light, not faster than the speed of light, to the Earth, which would feel these ripples after 8 minutes. So what general relativity predicts is if someone were to come, if a giant were to come and move the sun, it would take 8 minutes for the Earth to find out that the sun had moved, and this is consistent with special relativity. So general relativity makes gravity consistent with special relativity. In the process, also modifies quantitatively the laws of gravity. And these gravitational waves are not just have to do with giants and some of the other things that were actually very famously observed a couple of years ago. These gravitational waves are really things that exist in the universe and were observed by the LIGO observatory very famously a couple of years ago, as I'm sure all of you have heard. Okay. Let me say that general relativity also brings with it many other dramatic predictions. One dramatic prediction is a prediction of what's called a black hole. As said, there are some equations of general relativity, and now you can just go ahead and you can try and solve these equations and see what comes out of the solutions to these equations. And Carl Schwarzschild, very soon after these equations were developed, in fact, Jenner found this exact solution, which is called the Schwarzschild solution, which is a certain solution to the equations of general relativity, and in fact was not taken as seriously as it should have been till much later, till the 1970s, till 50 years after he developed the solution. And this solution is what's called a black hole solution. And what a black hole looks like is like this. Black hole looks like some region where you have the sun. Remember I said the sun was causing some warp in the fabric of space-time. But a black hole, in a sense, causes a tear in the fabric of space-time. So the way you should think of this fabric of space-time in the neighborhood of a black hole is that you have this tear in the fabric of space-time. It's some region where gravity has become so strong that nothing can escape, not even light can escape. And therefore, there's a horizon, and once even a ray of light falls into it, it can't exit, it must only go inside the horizon, and then it goes all the way up to the singularity at r equal to 0. Where it ends its life. Okay. So this is a solution that is very important in studies of gravity and also in studies of quantum gravity, and this is what is called a black hole. So when you hear about black holes in the popular media, what people are really talking about are some solutions to the equations of motion of general relativity, and the key characteristic of these solutions is that they have some region, this region where the boundary of the black and the red is, which is called the horizon. This horizon is the region from which nothing can escape, not even light. Okay. So now I said to you that in this whole notion of in this outline, this superstructure of fundamental physics that I showed you, there was one main physics which I covered in the beginning, and then there was relativity, and now I want to come to an even more dramatic entry in this register, which is the notion of quantum mechanics. So let me try and describe that. And then at the end, we'll try and tie all of these different threads together. By the way, I should say that the way I've structured this talk, there's a lot of separate ideas which I'm trying to introduce you to. So in fact, the stuff I said about relativity is largely unrelated to the stuff I'll say about quantum mechanics, although I'll tie them together later. But one important consequence of this is that if you've been sleeping for some time, you can always wake up at any point in the talk and then start paying attention. So you will follow the talk from there on. So you can wake up now and follow the bit about quantum mechanics, even if you got lost in the bit about relativity. Okay. So quantum mechanics was developed in the 20s and the 30s, and it was developed by Bohr. There are many people who are associated with this. There was Bohr and Schrödinger and Heisenberg and Dirac and many others, too many others to list on this slide, but there are many people who are associated with this. And the key thing, remember I said that all of these things came with some paradigm shift in the way we view the world. And the key thing that quantum mechanics forces you to modify is it forces you to modify a notion of what is real, what is real in the universe. And the most dramatic illustration of this is what's called Schrödinger's cat. Okay? So Schrödinger's cat is the following state. It's a state in quantum mechanics. It's a state, it's very hard to make the state with real cats, but as I'll describe in a minute, you can do it with other systems. But it's a state in quantum mechanics where you have what's called a superposition of a cat being alive and a cat being dead. Okay? So now, in everyday life, you would think that this is not something that's possible. How can you have a cat being both alive and both dead? What quantum mechanics tells you is that you can have a state of this kind, and what this means in practical terms, what this means is if you try and measure and try and see whether the cat is alive or the cat is dead, then with probability half, you will find that the cat is alive, and with probability half, you will find that the cat is dead. And this is a completely probabilistic process. But if you try and ask, is the cat really alive or is the cat really dead, then there is no answer to that question. The answer to the question is the cat is both alive and dead. It's in a superposition of being alive and being dead. And of course, that's something that's completely antithetical to our usual mundane notions of reality. Right? We think this bottle is either here or the bottle is here. But in quantum mechanics, you can have a situation where the bottle is both here and here. It's in a superposition of being here and being here. Now, the reason we don't observe these very funny effects in everyday life is because, for large objects, it's very hard to prepare these kinds of states. These kinds of states, in a sense, tend to decohere very fast. That's the technical way of saying it. But the statement to remember is that it's very hard to prepare these kinds of states. Although there is a very nice series of books called Mr. Tompkins, written by, and this Mr. Tompkins series of books tries to explain what would happen if these quantum effects started appearing in real life. If in real life, for mundane objects, for everyday objects, you started having these superpositions, then how life would be completely different from the way it is. So therefore, quantum mechanics is very explicitly not mundane physics. It's not something we see, but it is indeed true that at the microscopic levels, sometimes things can be of this kind. So if you take, for example, an electron, which is actually a more realistic example, you can indeed have, so electrons have what's called a spin. So their spin can be aligned with the z-axis. They have a spin, and one simple way to think about it for the purpose of this talk is just to think of this bottle spinning, and you think of the axis of rotation. So this bottle can spin this way, or it can spin this way. Okay? And if it's spinning this way, then I'll say it's spin up, and if it's spinning this way, I'll say it's spin down. And you can think of electrons also as having a microscopic spin, and the spin can be either spin up, in which case it's aligned with the z-axis, or it can be spin down, in which case it's aligned with the negative z-axis. And the electron is a two-state system. And like the Schrödinger's cat, you can genuinely create superpositions of the electron, which are a superposition of being spin up and spin down. And what this means is that if you were to measure the spin of the electron, then with probability half, you would find that the electron has spin up, and with probability half, you would find that the electron has spin down. But if you try and ask me, really, is this electron in either spin up state or spin down state? There's no answer to that. And the answer to that is that this is a wave function, and if you do a measurement, I can tell you the probabilities, but the notion of reality that you have has to get modified. So this, I can't emphasize how strong a departure this is from our notion of reality, and this is not a mystical notion. This is really a very, very, very well-tested experimental theory, which tells us that at a microscopic level, the notion of reality that we have is different, and you can have electrons in superpositions of states like this. Now, this is actually very important for the notion of quantum information, that was in the title of this talk, and let me try and describe why. Okay. So now, instead of one electron, let me take two electrons. Okay, so here's electron 1 and here's electron 2. Now, these two electrons, you can check, can be in 4 possible states, right? They can both have spin up, this can have spin up, this can have down, this can have down, this can have down, this can have down, this can have up, or both can have down, right? So it looks like you have 4 possible states. But you can do something else. You can again create a superposition of these states of the electron, just like we did for the one electron state. And now you can get a superposition of the following kind. When the first electron has up, the second electron has down. And then there's another possible situation, which is when the first electron is down, the second electron is up. This kind of superposition is what's called an entangled state. It's called an entangled state because you see the spins of these two electrons are correlated, and there's no way to think of these two electrons as being independent systems. Okay? In a sense, they're always correlated with one another. There's no independent, if this is up, then this is down. If this is down, then this is up. So this is a phenomenon called entanglement, and you can easily persuade yourself the moment you have more than 1 degree of freedom, these kinds of entangled states are very generic. You can easily produce these kinds of entangled states. And remember, as I said, for those of you who are not familiar with quantum mechanics, don't get worried about the notation. What this plus means just is, if you measure the state, with probability half you would find that the first electron was up and the second was down, or with probability half you would find the first was down and the second was up. In this state I'm talking about, there's no probability for both electrons to be down or for both electrons to be up. Okay, so I've excluded, I've prepared a state, so I've excluded 2 out of the 4 possibilities. Okay. Now, there's a very dramatic consequence to the fact that you can have states of this kind. And the dramatic consequence is as follows. So let's prepare the state that we had in the previous slide. And let's have 2 experimenters. So let's take 2 experimenters who have these 2 electrons, and then they take, each of them, they have these electrons, they prepare them in the state, and then each of them takes one of these electrons, and one of them stays on Earth, and the other takes 1 electron, and this other person goes to Mars. Okay? So they have this 2 electron system which is prepared in the state, and one of them goes to Earth, the other goes to Mars, and then they measure their systems. So this person measures whether this electron is spin up or spin down, and then this person also makes an analogous measurement. When you do that, you find the following dramatic prediction of quantum mechanics, which is when these 2 people, one of whom went to Earth and the other went to Mars to make a measurement, when the first person finds that his electron is up, then the second person necessarily finds that his electron is down. And when the first person finds that his electron is down, then the second person necessarily finds that his electron is up. So the results of these 2 measurements are correlated. In fact, what is more, once the first person has made his measurement, and if the first person finds that the electron is either up or down, then the results of the measurement of the second person are fixed, are determined already. Even though the second electron is very far away, even though the second electron in a sense has gone to Mars. Okay. Even then, once the first person has measured the electron, you already know what the answer of the second person is going to be. This is something that bothered many people, in particular it bothered Einstein a lot. So Einstein and Podolsky and Rosen very famously wrote an incorrect paper on this, saying that the fact that this phenomena occurs, so this is a paper they published in 1935, and they very famously argued that this phenomena meant that quantum mechanics was wrong. But quantum mechanics wasn't wrong, they were wrong in fact about this. And this is really, because their argument was, you make a measurement on Earth, and how can it control what's happening somewhere else on Mars? It looks like you have non-local effects in contradiction with locality. And many physicists were uncomfortable with this prediction of quantum mechanics. But in fact, this is a simple consequence of the fact that you can produce these correlated entangled states. And we now know, and we have verified many times, that this prediction of quantum mechanics is correct. In fact, fact, if you follow the popular science media, you will many times hear experiments which keep testing these Bell's inequalities. Although in a sense, it's now there's nothing new about it, but people still continue to test these Bell's inequalities, which is basically a way of testing these predictions I mentioned before. And every time we find that the predictions of quantum mechanics are correct. And the reason that this is not inconsistent with locality and is consistent with relativity is as follows. You see, remember I said that you have these two people, they have the electrons, one of them goes to Earth, the other goes to Mars. Now when this person makes a measurement, he finds it's up, and it's true that completely determines what the result of the measurement of this person will be. But this person has no way of knowing what the measurement of the person on Earth was. So if you ask what are the probabilities that this person will obtain either up or down, those probabilities remain half and half. And that's because this person obtained either up or down with probability half. Therefore, this person will also obtain either down or up with probability half. So even though these two results are correlated, there is no way for the person on Mars to know that the person on Earth has made his measurement. So this is the key that's important in ensuring that quantum mechanics is consistent with relativity. And the statement is that even though these answers are correlated, if you think about it a little bit, you can check that the probabilities by the experiment at Mars are unchanged by this measurement that's made on Earth. Okay. In fact, there's a way of saying this. There's a way of saying this in terms of what's called the density matrix, which I won't go into. But the technical way of saying this is that the density matrix of the person at Mars is not modified by this measurement on Earth. Let me just say one more thing about the density matrix, which is why I introduced it. This density matrix is useful for asking these questions about probabilities, but it's also a useful way to measure this notion of entanglement. Remember I said that there's this notion of entanglement which exists for quantum systems with more than one degree of freedom, which tells us how correlated these systems are. And this density matrix, there's John von Neumann argued that this density matrix could actually give you a good quantitative measure of entanglement. Entanglement isn't only a qualitative notion, it's a quantitative notion. And you can calculate some number associated with the state that tells you how correlated these two systems are. So once again, for those of you who don't like the equation, don't worry about that. The statement is just that given a state of this kind which has correlations between the two electrons, there's some number you can calculate that tells you how correlated these two systems are. Okay. Now, let me say a little bit about quantum versus classical information and how entanglement makes quantum information and quantum computing completely different from the notion of classical computing. You see, instead of now 2 qubits, you can think of n electrons. Now, these n electrons can be in 2 to the n states. Because you have n electrons, the first, and here are the 2 to the n states. All the n electrons can be up, or maybe the last electron can be down, or maybe the second last electron can be down, or maybe all the n electrons can be down. And since each electron can be in one of 2 possible states, it's easy to verify that the set of all possible states in the system is 2 to the n. And if you just wanted to keep track of all of these states, you would get all you would need would be an n-bit binary system. So when you think about the way your computers function, this is how your computers function. You have bits of information. Each bit can be either 0 or 1. If you have n bits, that gives you 2 to the n states, because each bit can be 0 or 1, so that has 2 to the n possibilities. And therefore, in a classical system, you would be able to keep track if the electron was in one of these possible 2 to the n states, or if the system of n electrons was in one of these possible 2 to the n states. Okay. But remember that quantum mechanics is different. You can also look at superpositions of states. And in particular, this quantum mechanical system can get into an entangled state where you might have a sum of all the electrons being up, and then all the electrons being up except for the last one which is down, and then all the electrons being down. In fact, you can have not just a sum, you can also have systems of this kind where you put a minus sign here. Or maybe you change the probabilities. In this system, the statement is that with probability 1/3 you'll get all up, with probability 1/3 you'll get all up except for the last one, with probability 1/3 you'll get all down. But instead of 1/3, 1/3, 1/3, you could have changed those probabilities. And therefore, if you wanted to keep full track of the quantum mechanical system, you have to keep track of all the numbers that go in here. Okay? And all the numbers, there are 2 to the n numbers that go in here because there are 2 to the n possible states of the full system. And this is the most important feature that distinguishes quantum and classical computing. It's the statement that if you want to keep track of the information in an n-qubit system, you need 2 to the n real numbers. Unlike an n-bit system, right, where you just need n binary numbers, here you need 2 to the n coefficients to keep track of the information that lives in an n-qubit system. And that's why quantum computers are completely different from classical computers, because with n qubits you can do a lot more, you can do exponentially more than you can do with n bits. And the reason for this is as follows. It's because the number of states of n qubits is much larger than the number of states of n bits. For n bits you can only be in pure states. You can be in this or this or this. You can't be in these superpositions where you have some probability of being in this or some probability of being in this or some probability of being in this. And that's why quantum information is completely different from classical information. Okay, so now let me say a little bit about how you start putting these regimes together. So I talked about mundane physics and relativity and quantum mechanics, and now I'll start asking, what happens if you start putting these regimes together? One way in which you could put these regimes together is you can start asking what happens if you have particles which are very small, okay? And then you clash them together. If there's a tape missing here, if you take very small but very fast moving particles and you crash them into one another, then you can start what would happen in this situation. And for this you need to combine the predictions of quantum mechanics with the predictions of special relativity. Okay? And in fact, this is a phenomenon that doesn't require you to have any dramatic paradigm shifts like the kind you had for quantum mechanics and for relativity. This is a formalism called quantum field theory, which was developed again by many people, Feynman, Schwinger, Tomanova, Dyson, some of the people who are associated with this. But really it's just a question of systematically applying the principles of relativity and quantum mechanics, and it leads to a formalism called quantum field theory. And this formalism of quantum field theory is very useful. It's what you use in particle accelerators. You see, when you try and discover physics using particle accelerators, this is the kind of experiment you do. You take two protons, you take two proton beams, and you crash them to each other at very, very high energies. And this is what is done in this very famous Large Hadron Collider, which is in the France-Switzerland border, which many of you might have heard of. So this is a picture of the CERN, and this is a picture of this huge ring, which is 27 kilometers in radius, which straddles the border between France and Switzerland. And in this ring, they do these experiments where you take very small objects which are very fast moving, and you crash them into one another, and then you need this phenomena of quantum, we need this formalism of quantum field theory to understand what will come about. Okay, now I'm not going to say much about quantum field theory, but let me just try and say one thing that we learned from quantum field theory. And this is just a simple algebra and something useful to keep in mind whenever you think about fundamental physics. The statement is that if you want to probe a distance delta x, if you want to probe a small distance by crashing particles into one another, then you need at least an energy, okay, which goes inversely with delta x. Okay. So if you want to probe very small distances, you need very high energies. And the reason for that is that when you crash particles into one another, these particles have a de Broglie wavelength. And this de Broglie wavelength becomes smaller as you increase the momentum or the energy of these particles. And therefore, if you want to resolve physics at very small distances, you need these particles to have very small de Broglie wavelengths. And this requires you to accelerate these particles a lot. So there's an inverse relation between the distance that you can probe and the energy that you have. So in particular, you might have heard that this Large Hadron Collider, the picture I showed you previously, can go up to energies of order 13 tera electron volts, which are very, very high energies compared to what we encounter for fundamental particles in everyday life. And this tells you that this Large Hadron Collider can probe distances of up to 10 to the minus 19 meters, okay, but not smaller than that. Okay. And this is one thing that we learn from quantum field theory. Okay. Now, let me say a little bit now about quantum gravity, and I'll use the fact I just mentioned when I come to that. So why is it that quantum gravity is so hard? There are many reasons why quantum gravity is so hard and why we don't have a theory for quantum gravity. Before I go there, let me just try and say, so far I've talked about stuff that we understand very well, and now talk about stuff that we don't understand very well. And I'm going to come to this part about quantum gravity, and let me try and explain why it is that we don't have a good theory of quantum gravity. Why is it that we can't put together quantum mechanics, which I talked about here, and general relativity, which is a theory of gravity. So I'm going to try and explain in heuristic terms why it is that quantum gravity is so difficult to build a theory of. So here's one reason that quantum gravity is difficult to build a theory of. It's the fact that remember that the attraction between two particles in gravity is controlled by the product of the masses between them. In fact, you can check that in quantum mechanics as well. If you take two particles and they are interacting gravitationally, and you ask what is the strength of quantum effects as compared to classical effects? Okay, that's a well-defined question you can ask. You can ask how important are quantum effects as compared to classical effects. So as I said, in mundane physics, for example, they are not important if you do these kinds of experiments. But you could ask, if you did a particle physics experiment like this Large Hadron Collider, how important are quantum effects compared to classical effects? That ratio is controlled by some number, I'll call that number G, and that number turns out to be proportional to the product of the energies of these two particles. Multiplied by some constant, this is the Newton's constant, this is the Planck constant, which is the speed of light. But basically the thing you need to remember is this number goes like the square of the product of the energies of these two particles. So in particular, if you wanted to probe very small distances, remember I said that to probe small distances you need high energies. That's one thing we learned from quantum field theory. If you wanted to probe very small distances, then you could ask, how important would quantum gravity effects become? And you can check that if you wanted to probe distances that was smaller than 10 to the minus 33 centimeters, okay, then quantum gravity effects would become very important and gravity would become strongly coupled. So unlike many other theories, which in fact as you go to very short distances become weakly coupled, gravity is a theory that becomes strongly coupled at high energies, which tells you quantum gravitational effects become more and more important as you go to short distances. So, this distance I should emphasize is much smaller than the distance we are probing at current particle accelerators. But if you wanted to understand physics at very short distances, then gravity has a property which is different from that of other quantum field theories, and that property is that it tends to become very strongly coupled. So, if you are at very large distances, gravity is a very weak force. It's a weak force, for example. So, for those of you getting lost in the technicalities, the gravity is a very weak force in everyday life because the fact that I'm lifting up this pointer means that with the electromagnetic forces in my hand, I'm actually acting against the entire force of gravity of the Earth. All of the Earth is trying to pull this pointer down, but I'm still winning in pulling it up. And that's because gravity is such a weak force compared to the electromagnetic forces that act between my hand and this pointer. But what this formula tells you is that as you go to higher energies, or as you go to very short distances, gravity will become stronger and stronger, and eventually it will become much stronger than electromagnetism. And at this distance, which is called the Planckian, gravity will become the strongest force, much stronger than all these other forces, even though at mundane distances, gravity is much weaker than other forces. So this is one reason that makes gravity hard, the fact that gravity has this behavior that it tends to become stronger at short distances. But gravity also has another feature, which has to do with this formation of black holes that I told you about. This feature is that if you take two particles and you crash them not at this Planck energy, but at much higher energies in the Planck energy, then gravity simplifies again. And then we know what happens. What happens is you get a black hole. Okay. So if you take two particles and you give them this Planck energy, it's very hard to say what will happen because gravity is becoming strongly coupled. But if you give them much more energy than that, then in fact the answer is very simple. We already know the answer, and the answer is that you will get a big black hole. So gravity has these funny features. First, it behaves differently from other forces in that it tends to become stronger at short distances. But once you go to very high energies, then gravity again becomes a simple force. So really, the question is as follows. Can you find any theory which does the following? It correctly reproduces Newtonian gravity at large distances. The mysterious force of quantum gravity that acts on the screen green makes it vibrate. but the question is, you want to find any theory that can interpolate between these three regimes. Okay? It correctly gives you Newtonian gravity, the force between the sun and the earth for mundane types of experiments. It correctly gives you the strong coupling and correctly explains what that is when you go to the Planck scale. And it correctly reproduces the physics of black holes when you go to very, very high energies. So really what you want is some theory of gravity that will correctly interpolate between all these three regimes. This is some prediction of just mundane physics. This is a prediction of quantum field theory, the fact that it becomes strongly coupled near the Planck scale, and this is just a prediction of general relativity. Now when you first see this as a graduate student, I have to say that when I was first a PhD student and I said, this is the problem of quantum gravity, I said, no, what's the big deal? Let's just sit down and write some theory that will do this. It may or may not be the theory of the real world, but we'll just write down a theory that will have these properties. If someone tells you find some theory to explain some phenomena, you can always come up with a dozen theories. Whether or not that's the correct theory is a different question. But if someone says, find a theory to explain why something happened, I can always give you some reason. And so I thought, when you first see this, you say, oh, you have to find a theory which has these three properties. So we'll just write down the theory of quantum gravity. But that turns out to be remarkably hard. It turns out to be very hard to try and construct a theory that has these properties and doesn't have some other very bad internal inconsistency. Okay, now I don't know of any simple way to explain this, except that you should try it. You should try writing down a theory that has these three properties, and you will find that it's remarkably difficult to construct a theory of quantum gravity. So this is, gravity is hard because it requires you to fit all these different things you know about gravity from other theoretical considerations, and it just turns out to be very hard to find a theory that's consistent with all of these considerations. And it's something that physicists haven't really succeeded in doing despite a couple of decades of effort. But we succeeded in building some toy models of gravity. Okay, so let me describe some toy models of gravity. So we've partially succeeded in building theories of quantum gravity. And the most successful efforts so far have come from a field called string theory. And the most successful formulation of quantum gravity in string theory is as follows. I'll just sketch it to you. You think of quantum gravity in a box. This box is technically what's called anti-de Sitter space. But forget about that. Just think of quantum gravity in a box. In this box, actually, on the y-axis, you have time running. So really, the spatial surface is only this little disk. So you have a disk, and then I've plotted time on the y-axis. So think of quantum gravity in this little disk, and then it turns out that if you set the boundary conditions right, in this toy example, which is not quantum gravity in our universe, right? Our universe is not some box. But if you were to think of quantum gravity in this toy setup, then it turns out you can understand quantum gravity. You can understand the quantum gravitational interactions of these blue particles as non-gravitational interactions, as interactions in some other theory which doesn't have gravity, that live on the boundary of this box. And this is called holography. It's called holography because it's holographic in nature. What's a hologram? You take some three-dimensional picture and you project it onto a two-dimensional setup. This is what's happening here. You have gravity that's living inside this box, and somehow the gravitational dynamics inside this box can be described by some non-gravitational dynamics on the boundary of this box. And because we know how to understand non-gravitational quantum field theories, we can use that to explain and understand the gravitational dynamics that goes on inside this box. Okay? So this is the trick of holography. You take a problem which is very hard, and you find a duality, you find a map to a problem that you understand well. So in this toy model, when you take quantum gravity inside this box called anti-de Sitter space, we do understand how to construct models of quantum gravity. This is of course only partial success. It doesn't tell us how quantum gravity in our universe works, but it does give us a good toy model of gravity, which has many lessons to offer us, as I now described in the last 5 or 10 minutes of the talk. Okay? So in the last 5 or 10 minutes of the talk, let me now try and describe some of the lessons this toy model of quantum gravity offers us, and in particular some of the very interesting relations to quantum information. Remember I said that quantum theories have this feature of entanglement. Okay? Entanglement is a statement of how correlated different parts of the theory are. It's something that's special to quantum mechanics. And what this duality of holography does is it takes this phenomena of entanglement that lives in this quantum theory that lives on the boundary, and it turns it into some geometric phenomena of gravity in the bulk. Okay? So it's taking some quantum phenomena and it turns it into some classical phenomena of gravity. Okay? So let me just try and explain that. But try and keep this formulation in mind over the next few slides. What I'm going to now try and tell you is how this duality of holography converts this very mysterious phenomenon of entanglement into some rather familiar geometric phenomenon in gravity. Okay. So in particular, the fundamental formula, I should say that in the next few slides are going to be ahistorical. I'm not going to try and explain things as they were discovered initially, but as things fall into the framework that I'm describing. So sometimes I'm going to take things that were discovered earlier and put them later in these slides because they fit better into the logical framework that way. So the fundamental phenomena here is as follows. If you think of some region on this boundary, remember I said that gravitational dynamics inside this box is the same as some non-gravitational dynamics or some degrees of freedom that live at the boundary of this box. Now you could ask, in the ground state of the system, for example, how entangled are degrees of freedom that live on this orange segment with the other degrees of freedom that live on this red segment? And remember that entanglement could be measured by something quantitative called the entanglement entropy, which remember I said for the simple two-state electron system was just log 2 in the state we were talking about. But in general, it's some complicated property of the quantum state. Now it turns out that this entanglement entropy can be measured by something very simple. It can be measured, it can be calculated by just thinking of a geodesic, the shortest path that goes from this side to this side, and just computing the length of that shortest path. In fact, if you're in higher dimensions, if you didn't have a disk but you're part of higher dimensional systems, then the generalization of the statement is that the entanglement between one part of this quantum system that lives on the boundary and another part of the quantum system is just computed by the area of the minimal surface that interpolates between these sides. Okay? So it's some very simple phenomena that tells you that some complicated quantum property of this system, some complicated quantum information property of this system on the boundary is converted to some simple property in this bulk, which is some simple geometric property. Okay? This is actually very useful because you can use it not only to learn about entanglement, but you can also use it to learn more about geometry. Okay? In particular, remember I said that the bulk gravitational theory the bulk theory is some theory of gravity, this theory that lives inside the box. And one of the things I told you at the beginning of this talk was that this theory of gravity is controlled by these Hilbert-Einstein equations that tell you how the curvature of space inside depends on the distribution of matter. In fact, it turns out that you can use the entanglement of different regions on the boundary with each other to explain, to completely get these equations. Okay? So let me just try and explain that. That's not something very hard. You see, what the entanglement of the degrees of freedom on the boundary tells you is what the area of minimal surfaces in the bulk of this box is. But if I know the area of all sorts of minimal surfaces on the sheet, for example, if I know the area of all surfaces on the sheet, I can use that to completely understand the geometry of the sheet. See, there is something that's very intuitive and simple. I could tell you that I take this sheet and maybe I curve it up in this way. Now, there are two ways to describe it. First, I could try and tell you what the height of the sheet is as a function of x and y. Okay? That's one way to describe what the geometry of the sheet is. But alternately, I could give you that information in a more indirect form. I could try and tell you what's the area of different circles at every part of the sheet. And if I tell you the area of circles in every part of the sheet, it's easy to convince yourself that you can use that to back calculate what the geometry of the sheet is. And because this formula I told you relates entanglement to various areas in the bulk, you can use it to back calculate what the geometry is. And we have some other statement about the geometry, which is that the geometry is controlled by these Hilbert-Einstein equations. And indeed, these two things turn out to be exactly consistent with one another. So you have some totally different phenomena, which is a phenomena about quantum entanglement, which you can use to relate to something completely different, which is these Hilbert-Einstein equations and something geometric. through this formula that tells you that the entanglement entropy of some region in the boundary is given by some area of the surface of the bulb. So I know I'm being fast here, but I hope that the intuitive notion is clear. So the intuitive notion is just that you have some quantity, it relates it to some notion of the area, and the area is related to geometry, and geometry is controlled by the equations of general relativity, and all these things are consistent together. Okay. Now, in fact, you can find even more dramatic examples by using entanglement to understand the bulb. For example, you could try and construct different kinds of quantum states of this non-gravitational system on the boundary. One thing you could do is you could take two copies of this non-gravitational system and you could entangle them together in some particular way. This particular way is something that's familiar to condensed matter physicists and statistical physicists. It's called a thermophile state. There is some particular kind of superposition of states. Remember, I said entanglement has to do with taking superpositions of states. So if you take a particular kind of superposition, you can ask what is the kind of geometry you get in the bulb. And the kind of geometry you get in the bulb is something very exotic. It's a geometry which has two sides. Both of these sides are cut off by some box, and then there's a wormhole in between them. Okay? So you get two regions of space, both of which look like much like the space that we see around us, and then there's a wormhole that connects these two regions. So space. Here's another way to understand this. You have this left region of space, which is one of these regions. You have this right region of space, which you can think of this region. And this picture is showing you a cross section at a given instant of time of what this geometry looks like. And what this geometry looks like is that there's a left region, which is like our universe. There's a right region, which is like another universe. You have these two universes, and then in between them you have a wormhole, which connects these two universes. It's actually very important that the wormhole doesn't actually let you travel from one universe to the other universe. And that's because if you try to travel between one universe to the other universe, this wormhole kind of closes up and crushes you. You can see that from this diagram where time is drawn on the y-axis, and that's because the boundary of these wormholes are light rays. So anybody who travels has to travel slower than the speed of light, which in this diagram means traveling at an angle which is less than 45 degrees. And so anybody who tries to actually use this wormhole, you see this wormhole open up, and you think, I'll jump in and I'll see what's on the other side of the wormhole. But in fact, you never reach the other side of the wormhole. Rather, what happens is you get crushed as the wormhole closes up in this singularity, which is drawn by light. Okay? So you get these very exotic geometric phenomena, and these very exotic geometric phenomena have to do with some structure of entanglement in states of this kind. Okay, so I once again, for those of you, I'm not expecting all of you to get the details. The point is just that you get these very interesting and exciting kind of geometric phenomena. Once again, we're studying entanglement, and as I said, entanglement is a fundamental property of quantum information in the boundary. Okay, let me just say a couple of things and then I'll conclude. There's one more paradigm shift. So far I kept talking about paradigm shifts that came about with relativity and quantum mechanics. In fact, this whole notion of entanglement in geometry brings about one more paradigm shift. And the paradigm shift it brings about is something I also spoke about in the last talk, for those of you who were here, is that it tells you that so far we've been talking about this fabric of space-time. But if it's really true that physics is holographic, that somehow the dynamics of this fabric of space-time can be described by something on the boundary, then in fact it can't really be that this fabric is continuous. And the reason for that is that you see the total number of degrees of freedom in this gravitational theory that I was talking about are entirely described by some degrees of freedom that live on the boundary. And therefore the and these threads of space-time limit the fundamental information carrying capacity of the space. Okay? So let me try and make this, try and give you one consequence of this. You see, one consequence of the fact, if you were to say that the fabric of space-time is made up of a large number of threads, is as follows. See, imagine somebody who was here. So imagine somebody who was here and who made some local action here. If the fabric was some continuous fabric where different parts of the fabric were really disconnected, then as we discussed previously, it would take ripples in this fabric for the effects of these actions to propagate outwards. But one notion, if you think of the fabric as being made up of these threads of space-time, then that tells you that the information that lives here can also be captured at that same instant by making measurements on the boundary. Okay. So this in fact brings us halfway back to the kind of non-locality that we started with. It tells us that in fact, even though we think of space as being really local, in that something that some degree of freedom here is different from some other degree of freedom here, if you take seriously what these toy models of quantum gravity are giving you, then one of the things they're telling you is that degrees of freedom of different parts of space-time are not really exactly independent. They are approximately independent, but if you make close enough observations, then in fact some degree of freedom that lives here can be captured by by a very large number of degrees of freedom that all live far away. Okay? So to say this another way, if we go back to this example where we have this giant who's trying to move the sun, the statement would be that if you were to surround the sun by a lot of detectors, by very, very large, in fact you can calculate it for the sun, you would need 10 to the 77 detectors living within some small radius of the sun. But if you could set up so many detectors, then in fact you would instantaneously be able to detect that the sun had moved. Okay? So these toy models of quantum gravity, in fact, tell you that this notion of locality that we were taking very seriously and that in fact led us to relativity and general relativity may in fact need to be modified. And once again, I emphasize that this is something that's not relevant in mundane physics. Okay? This requires very, very, very fine measurements, but in fact it's something that's again conceptually, from a paradigmatic point of view, again important. Okay, so I'll stop here. Let me just go back to the slide that I said at the beginning. Once again, as I said, there were a large number of ideas, and I hope I managed to communicate at least 15 or 20% of them to all of you. And I hope that some of you will be interested and will go back and look up all of these ideas. But let me just try and remind you what I talked about. So we started by talking about mundane physics, and I talked about how when you look at high speeds and strong gravity, you have to modify the mundane notions of space and time that you have. And then when you look at very small objects, you have to modify the notion of reality that you have, and that brings you to quantum mechanics. And then you can start asking what happens if you have small objects at high speed, that brings you to quantum field theory. And then you can start asking what happens if you have small objects in strong gravity, and that brings you to quantum gravity, which we don't really understand very well, but we do understand some toy models of quantum gravity. And these toy models of quantum gravity are already telling us some very interesting things. Some of these very interesting features come from a consideration of quantum information and of entanglement. And one of the things in particular that these features tell us is that notions of locality that we tend to take so seriously, especially after the discovery of relativity, may only be approximate and not exact. Okay, so I'll stop here.
Excuse me, please sit down for a minute or two. Please do sit down. You heard a wonderful lecture.
5 minutes. It
was really a wonderful lecture, Professor Raju. Even though you started saying the lecture is a few subject and a few topic, you were successful in making it acute. At superficial level, you covered classical physics, quantum mechanics, relativity, and quantum gravity. I mean, the physics of macro and micro world. The profound concepts of quantum physics, just like quantum entanglement and other, were explained in a very simple and elegant way. It was inspiring lecture, and it was a beautiful lecture as well. I thank you on behalf of the Bangalore Science Forum and on behalf of all of us here. Now,
So my name is Som Shekhar, first semester BSF student. We consider the universe as three-dimensional space, isn't it? But why do you consider the fabric of space and time to be bent only along the horizontal plane? Why not along other planes?
That's because I can't draw in 4 dimensions. That's just because I can't draw in 4 dimensions. And that's just a drawing. You're right. The fabric, everything is curved in 4 space-time dimensions, but I can't draw 4 dimensions. I can only. So I want to draw a curved space. So first of all I need to embed it. Okay? And I'm only I'm only trying to draw two-dimensional figure because that's the limit of my.
Because of your convention,
it's not a question of convention. How can we can't, our brain is not evolved to picturize four-dimensional curves, right? You can picturize it mathematically. But if I ask you to draw a picture of a four-dimensional curve manifold, you can't do that, right?
Okay. Already.
My name is Partha Chowdhury. I am retired electrical engineer. But I am wondering in all this physics. I am not much enlightened, but I have some basic doubts. So what is this unified theory Einstein was telling? That is number one. Number two, this entanglement looks like something like a consciousness. If this is one spin of one electron is done, something on the Mars is getting affected. But the person on the Mars will not know whether the experiment is really done or not. That's what you were telling me. Is it?
No, not quite, but please go on and I'll answer the questions to you.
Thank you.
Okay, so the unified theory, let me say at first. This was a project that Einstein had in the beginning where he was trying to put together, gravity and electromagnetism and all sorts of things in terms of some unified classical theory. He was trying to put them on the same footing and trying to make many, electromagnetism and other forces also appear as geometric forces within gravity. That's not a project that's really gone anywhere. So that project was never taken up very seriously by the rest of the theoretical physics community. Now, at some point in this study of quantum gravity, people thought that quantum gravity would give you some theory of everything, which would predict everything. And that project, in a sense, has also not succeeded. So, unified theory is that I tend not to take very seriously, even though you'll hear talk about that a lot. But really, we have these different physical phenomena. We have electromagnetism, we have the strong magnetic forces, we have gravity. We need to understand these forces and their quantum mechanics separately. And of course, once you have a theory of all of them, you can put it together. That, if you like, would be a unified theory. Just like you can have a theory of light and the weak and strong force. But there's nothing mystical about it. It's not that this unified theory is the only theory that the universe could have been. That somehow mathematical consistency picks out this only theory. So that project is not a project I have a lot of sympathy for. The other thing, entanglement has nothing to do with consciousness. Really the statement is that the person who lives on Mars has with him one electron. The real way to describe that electron is in terms of a density matrix, because that electron is not in a pure state. That density matrix is actually unchanged by the experiment that the person makes on Earth. So it's not really that the electron here is affected. It's not that the electron on Mars is affected by what happens on Earth. It's true that the result of the experiment on Earth and the result of the experiment on Mars are correlated. But that's not because the experiment on Earth in some way affects the experiment on Mars. In fact, to the contrary, the experiment on Earth does not exert any physical influence on the electron in Mars. Nevertheless, it's true that these things are correlated. And that requires us to indeed think about reality in a different way, to think about these wave functions and density matrices. But there's no physical effect that's propagating from Earth to Mars. I hope that answers your question.
So, thanks, wonderful lecture. I have a question. When some matter is sucked into the black hole, it's crushed to zero, what happens to the energy of that matter?
Or it gets added to the energy of the black hole. If you throw something into a black hole, you add to the mass of the black hole. So if you take the sun, it has some mass, which is 2 into 10 to the 30 kg. If you throw some more stuff to it, you'll get a bigger black hole. These LIGO experiments with sort of black hole merger, this is what happened. You had two black holes of different masses, they merged and they made a bigger black hole. So total mass is the sum of the masses.
I am Arvind, I'm studying first PUC, and my doubt is, you told that CERN super collides, you can actually accelerate two particles and create a black hole.
No, I didn't say that.
When you collide two particles, there is a black hole created,
He's got it.
Yeah, but people say that the mass of for a black hole to be created, there must be a particular mass of like 3 mass of sun or something like that. how was it created? Or
So no black holes are created at this large hadron collider. So it's true. I said if you crash two particles together with high enough energy, that energy is about 10 to the 14 times as large, or maybe 10 to the 16 times the energy that we actually have at the large hadron collider. So if you build an accelerator that was 10 to the 16 times as powerful as the accelerator in the large hadron collider, then you would be able to create particles. Then you would be able to create black holes in these collisions. The Large Hadron Collider, the CERN itself doesn't create any black holes. But it's not the case that black holes can form only for the mass of the sun. You can form black holes for very small masses. The moment you have a black hole, the moment you have the Planck mass, which is actually quite a small mass in every units, you can create a black hole out of that. So you could take this bottle and you could crush it into a black hole. You could take the Earth and you could crush it into a black hole. If you form a black hole, it would be 1 centimeter in size. It would be a very small black hole. You have to take all the Earth and crush it. You would get a small black hole. So, the smallest mass that your black hole forms is quite small. It's a Planck mass. It's not, the 3 times the mass of the sun is much, much larger. You can form black holes with smaller masses. The thing is that if you really wanted to form a black hole in an experiment, you have to take 2 particles and you have to bring them that close together. You see, you could in principle form a black hole out of the Earth, but to do so you would have to crush the Earth to within 1 centimeter. The forces that are required for that are huge. That's why if you really wanted a particle accelerator to create black holes, you have to create very high energies, so that 2 particles could approach within the distance of their spot shadow radius. They would be localized within that distance. But that would require something much bigger than the large hadron.
I have 2 more doubts.
Yeah.
What is the black hole information paradox theory? It's like the 2-dimensional print is upon the surface of the black hole, and when a black hole emits Hawking radiations, the information is like, I didn't understand.
So I talked about that in the last talk, a couple of months ago. The black hole information paradox is indeed the statement that once black hole form, if you add quantum effects, the black holes slowly evaporate, and it looks like the final answer that you get is thermal. But it's not really a paradox if you think about it very closely. It's the phenomenon of thermalization that you see happening in many other systems. If you take for example gas in this room, and you give it some, you take some red gas here and some green gas somewhere. So you wait for some time, they'll mix, okay? And then you won't be able to distinguish it will look like the final state you have doesn't have information about the initial state that you started with. Actually, I'll give you a simple example. You could drop some stone into this water, it could create some ripples, but after some time it could settle down completely. So it would look like this process is irreversible because you don't know what is the speed with which the stone fell in, because you have dissipation. So the stone is now just settled, and when you throw the stone in at 1 meter per second or at 10 meters per second, the final state looks the same. And this looks like it's in violation of the reversibility of physics, but it's not really, because if you keep track of all the atoms and everything, the information is always stored in that. So things look like they are dissipative, but they are never really dissipative at a microscopic level. And it's really the same answer to the black hole information paradox.
Hello sir, thank you for an amazing talk. But my question was, when we talk about an anti-de-Sitter spatial analysis, on a fundamental scale, don't we again come back to the problem of considering 2-qubit system, separating it to measure the non-local effects, and the problem of making measurements and forcing a certain outcome. So in this case, let's assume we're on the Earth, we're making our measurements, we have this model, and we're building upon that on a very firm mathematical footing. But we don't have anybody else on Mars to corroborate the same. So when you talk about the inferences that we obtain from a formalism of mathematics, which is a very subtle difference from what the truth actually may be, how exactly do we corroborate all these theories?
So I talked about many theories. The one about measurements have been corroborated in many experiments. You don't have to go to Mars to do it, right? Mars was an extreme example. You could take 2 bits and you could separate them by the length of this room, and you could still do this experiment. The experiments that test this prediction of quantum mechanics are called tests of Bell's inequalities. So if you can, and there are many experiments that have tested Bell's inequalities, which tell you there's a fundamental difference between classical and quantum predictions. And these experiments have been done. They're very easy to do. I can describe them to you. It's really some version of this experiment. You take two experimenters, you separate them by some distance. One experimenter is allowed to measure on whatever axis, not just the z-axis, and then the other experimenter is also his measurements. And you can check the predictions of quantum mechanics are correct. So these experiments are not so difficult to they're difficult to set up for an experimental point of view, but they've been done many, many times. So same for the experiment, same for everything I said about relativity and general relativity. These are things that have been verified in many setups. For example, general relativity has been verified very well by the recent LIGO discovery. Now, there are some things I said at the end about quantum gravity. For example, the duality, the thought models of quantum gravity that we have. Those thought models of quantum gravity, it's true, are not possible to test experimentally for reasons that I explained some time back. If you wanted to test them experimentally, you would need energies and forces that you can't attain with current technology. But let me say the reason we are interested in these thought models of quantum gravity nevertheless is also something I mentioned in the talk. It's the fact that these thought models of quantum gravity give us for the first time at least one mathematically consistent theory of quantum gravity. And this is a rather unusual situation. You see, usually we have many mathematically consistent theories, and then we can ask which one is the correct one, and you can check that using experiments. In this situation of quantum gravity, we have so far, with all our ingenuity, been able to find only one consistent model of quantum gravity, which comes from string theory. This is model of holography. And that's the reason we take it seriously. If tomorrow many other people were to come and find 20 different models of quantum gravity, all of which gave different predictions, then we wouldn't take these physical effects seriously. But it's the fact that because we are finding only one model, that we believe that in some sense the other things that we know very well, such as quantum mechanics, such as general relativity, such as quantum field theory, are also leading us towards certain predictions. This is not something that's so unusual also. For example, the Higgs boson that was discovered in the particle accelerator at CERN. It's something that in a sense people knew and expected for 50 years. Because from other things they expected that this prediction would come. The same with these gravitational waves that were discovered by LIGO. Because the theory was so well developed, we were not surprised that these gravitational waves existed. So, often you have some experiments and based on that you can make an inference, and you take that inference seriously even if you can't check it directly, because it's based on other experiments that you've done.
Alright, so despite the paradigm shifts, we can safely assume that these mathematical theories will hold even at such an advanced level.
Well, again, I don't know what such a... as I said, there are many parts of these theories, such as quantum mechanics and GR, that we've tested very well. And these are other robust predictions that are coming out of trying to put those parts together. So now, it could be that we're missing something. Of course, that's always possible. But the reason we take them seriously and we think about them all is because, you're putting together things that you understand well, so you're making an inference.
Now, one minute. I know large number of questions are there, but always to support any you want to ask 1 minute. After this question, I will close the session, but these people come to dais and ask you the question.
Thank you. Very good talk. Even though I don't have a background in physics, I was able to comprehend most of the things that you explained. So I have a very simple doubt, since we are at the brink of space exploration and to make humans
space exploration.
Yes, and trying to make humans an interplanetary species. This is again coming to talk about black holes. So since first is how do we detect black holes in space? Because we've just seen it in movies where they show a spaceship going in and then coming out through the other end, with obviously not, which is very hypothetical. And how do we prevent black holes, coming in the way of space exploration? Because we're launching rockets right, left, and center, and so that's my question.
So the way we detect black holes is actually an interesting thing. It's one of the things that astrophysicists spend a lot of time on. One of the ways before this LIGO discovery of detecting black holes was to look at their accretion disk. What happens is you can't see a black hole directly because no light escapes it, right? So you can't see it directly. But what can happen is you can see a lot of objects, a lot of stars circling something, and you don't see that something inside. But then you infer that when they're circling, they must be orbiting some central mass. And sometimes some of these, and so from that orbit, you can try and calculate what the size of that central mass is. And if that's smaller than some amount, then you believe that it's a black hole. Because that once the mass is squeezed smaller than Schwarzschild radius, it has to be a black hole. So the way you infer the existence of black holes astrophysically is really by looking at the accretion disk and by looking at matter around them. Because you might have also charged particles that are falling into the black hole, and as they fall in, they emit radiation. You can capture that radiation. Using that, you can discern various parameters of the black hole. Now, the LIGO experiments gave us a different way to look at black holes. Because in LIGO, they look at black hole mergers and they look directly at the gravity waves that are being emitted from these black hole mergers. They're not looking at electromagnetic waves that are being emitted by accretion disk. And so that's one more way you can detect black holes. So we have various ways now of detecting the presence of black holes. But black holes are not really that dense. If you were to throw something in, if you were to launch some rocket in the galaxy, first of all, we have so far not even managed to go anywhere near our solar system. Space is really immense. Okay, and if you launch a rocket somewhere in the galaxy, the chance it will fall into a black hole is really very small. So you should remember. One thing I think about when you think of this is there was this Malaysian Airlines plane that fell into the ocean. And all the king's horses and all the king's men, all these countries together are not able to find it. They're not able to find it because the ocean floor is immense. You have a big plane, it falls on the ocean, and the ocean is really very big. And even if you look very hard, the plane is like a needle in a haystack. It's very hard to find. The galaxy and the universe are much, much bigger. So there's most of it is just empty space. So it's not like there are black holes keeping around ready to swallow our spaceships as we said about. But this is of course a hypothetical question because we are exploring, just the neighborhood of our planet really. You're not exploring large sections of the galaxy or anything. So yeah.
Okay, thank you. You can come in. Speaker about it. That was really good. Excellent. Any questions?